What's up, guys? Another video on ionization energy. This time we're looking at successive ionization energy. What is that? So very simply, it's the energy required to remove electrons, subsequent electrons from different ions. So we're basing most of this video on magnesium. So let's look at some definitions there. So if we looked at the second ionization energy for magnesium, our definition there would be the energy required to remove 1 mole of electrons from 1 mole of gaseous 1+ ions to form 1 mole of gaseous 2+ ions. If we were asked to do an equation for that, it would look like this. We've got Mg plus gaseous, state symbols are important, reacts to make Mg2+ gaseous plus E minus. And if we were doing third ionization energy, it would be a 2+ ion that we start with and a 3+ ion that we end up with, and so on and so forth. What we have here is a graph of what that looks like, and hopefully we can see straight away a few things that I might want to draw your attention to. So our first thing is this jump here. We've then got a mini jump here and then a larger jump here again. And hopefully it's very obvious to you, particularly when looking at this atom, why we have this jump. There we remove 1 electron, 2 electrons, and then when it comes to removing that third electron, this is why we get the jump. Because now we're in an electron shell much closer to the nucleus. So here we're closer to the nucleus, to the positive nucleus, with less shielding. So greater attraction. Right? And as we go along, we can see another little jump here. So there, 1, 2, 3, 4, 5, 6. When we have our jump here, we're moving from an electron in the p orbital to s orbital. And this is a little piece of evidence that we have these subshells. And then we get our final jump here. That's when we're moving electrons from the innermost shell. So our explanation there will be exactly the same as our previous one. Okay, so let's have a look at another example. So here, again, just have a little think. Where do we see our jumps? I think we've got 2 here, right? We've got 1 here and we've got 1 here. Now our most common question is going to be for us to identify what group something's in. It's going to be very easy for us to make the mistake of this little jump. But again, we've seen here that our little jump is showing us where we're removing not a p electron, but an s orbital electron. So we almost have to ignore these little jumps and look for these slightly bigger ones. So there straight away, I can see a big jump between the 6th and the 7th ionization energy. And that's going to tell me that we're in group 6 for this element. something for you to give a go. Sketch a graph of successive ionization energies for nitrogen. Again, use your periodic table to help here. Think about where we're going to get that little mini P to S jump, and then when are we going to get the big jump when we're moving it, removing it from the innermost shell. An explanation would be great as well, and then write some equations for the first 3 ionization energies for nitrogen. Looking back at the previous video, first ionization energy of magnesium, again it's going to be just the same as this, 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous ions. In terms of the equation, be Mg plus, the state symbol is essential, reacts to make, sorry, not Mg plus, just Mg, reacts to make Mg plus, that is gaseous, plus E minus. So here, B and C is going to be C. Reason why? More positive nucleus plus smaller atomic radius, therefore greater nuclear charge, greater nuclear attraction, sorry. Next, lithium and sodium. Again, looking at our periodic table, we've got lithium and sodium. That's going to be lithium, isn't it? Again, this time smaller atomic radius, therefore stronger attraction. And the last one is P and S. This is one of our exceptions. So here, remember P and S is going to be P. And there we're going to talk about our we've got, if we quickly write our electron configurations, so there we've got Ne, and then we've got 3s2, 3p1, 2, 3. And for sulfur, again we've got that Ne, 3s2, 3p4. So it's the electron repulsion here. Leads to lower ionization energy. So again, whenever we're answering these, we're thinking about, first of all, is it one of our exceptions? If not, we're thinking about moving along the period or moving up the group. Happy revising, thanks.